We have seen that two-party cryptography is extremely useful. It concerns any task where Alice and Bob themselves don't trust each other. For example, secure identification. Clearly, it is highly desirable that we can solve such problems, that we can design protocols that solve such tasks for us in practice. Unfortunately, as we've seen, not even quantum communication allows us to solve arbitrary two-party cryptographic problems. The reason why these problems are more difficult than QKD is because here we just have Alice and Bob. They don't trust each other and need to fend for themselves. Unfortunately, Alice and Bob are no longer friends who can work together to check on Eve. So what can we do? Up to now, we have always assumed that the adversary is all-powerful. Eve had an arbitrary quantum computer in quantum memory, for example. Indeed, we allowed the adversary to control the entire universe, anything outside the labs of the honest parties. This week, we will be somewhat less paranoid. In particular, we will make assumptions. Assumptions on how powerful the adversary can really be. Of course, this means that our protocols will only be secure if these assumptions are satisfied. But in practice, this is a small price to pay to do the impossible. And since we do want to solve problems like identification in practice, one is willing to accept such assumptions. So the question that I want to discuss with you is what kinds of assumptions could we possibly make? To get some inspirations for this, let's briefly revisit the impossibility of the very simple task of bit commitment. Remember that bit commitment has two phases. In the commit phase, Alice puts a bit B that she wants to commit herself to in an envelope, and Bob is notified that she's done so. In the open phase, Alice reveals the bit B to Bob. And we had two conditions, which are summarized informally here, namely, Alice cannot change her mind about the bit B after the commit phase, so she's indeed committed to B, and at the same time, Bob cannot learn the bit B before Alice actually opens the envelope. So how could we evade impossibility? Let's have a look at the state of affairs after the commit phase is over, assuming that Alice and Bob just followed the protocol. At this stage, they share a state, rho AB, that depends on the bit B that Alice wants to commit herself to. Now remember the impossibility argument. Bob should not gain any information about the bit B. So we want that his marginal states, rho B corresponding to a commitment of 0, is exactly the same as the state that he has if Alice committed to a 1. But now by Ullmann's theorem, we knew that there exists some unitary, some operation, that Alice can apply to the purification to change her mind. So Alice has the purification, which I will call P here, of the state rho AB, and she can apply this unitary. And what this does, it transforms the state from the state where she committed a 0, say, to a state where she committed a 1. We could also go the other way around. To find good assumptions, let's see how we could break this impossibility argument. The first option is, of course, that maybe the states are not actually the same. That is, the state that Bob holds, if Alice committed a 0, rho B 0, and the state that he holds if Alice committed a 1, rho B 1, could be perfectly distinguishable. So that an all-powerful attacker Bob could in principle learn Alice's bit B before the open phase. Of course, this is not desirable if we actually want a commitment. So what can we do? We could make an assumption that even though the states are maybe perfectly distinguishable, Bob lacks the ability to do so. Maybe he would need very powerful operations or perfect quantum memory, and we will have a look at some concrete assumptions shortly. Another assumption would be to say that yes, maybe the states are the same, so there should exist this unitary. However, maybe Alice cannot perform arbitrary unitaries. Maybe Alice does not have a quantum computer. That is, even though she could in principle cheat, she cannot implement the cheating transformation U. Finally, another way to evade the impossibility argument is if Alice does not in fact hold the purification of the state. That is, the state that Alice and Bob share is actually not pure. This can, for example, be because they received some very special shared randomness for a third party. In this case, the third party holds the purification. Clearly, receiving some magical randomness from someone else is not the most realistic of assumptions, which is why in this video we will focus on options 1 and 2. In a separate video, however, we will have a look at a fun toy protocol that exploits option 3. Before investigating what precise assumption we can make that limit Alice and Bob's abilities to cheat, let's first establish some criteria that useful assumptions should satisfy. First, we need to be able to actually run the protocol. So whatever we are going to assume, it should be easy for honest Alice and honest Bob to execute the protocol. Second, we need to think about what an adversary would need to break the protocol. It would make no sense if the honest parties have it just as difficult as the adversary. In fact, ideally we want that much more resources are required by the adversary to break the protocol than we need to actually run it. If you want, think of the price of such resources. If the honest parties would need to pay $100 to buy hardware to run the protocol, would you feel safe if the adversary can break it with hardware that costs merely $200? Ideally, of course, the hardware and capabilities needed to break the protocol are even outside the reach of current technology. Finally, we want to think about what happens if at some later point more resources become available to the adversary. For example, maybe now the adversary does not have a quantum computer, but in a few years from now he could buy one. Or maybe now the adversary cannot store more than a handful of qubits, but tomorrow he could invest in a large quantum memory and store thousands of them. The question to ask is then, can the adversary still break the protocol retroactively? Or in other words, does security remain guaranteed even if the adversary later gains additional powers? Ideally, of course, we want security to last forever, or at the very least, as long as our secrets need to be protected. So let's have a look what kinds of assumptions we could now actually make. I will just give you some examples of such assumptions here, and you can find more pointers in the lecture notes. First, we could, of course, consider limitations on the operations that the adversary can perform, or on the time that these operations can take. Such assumptions target options 1 and 2. We could apply them for both Alice and Bob. Let's start with some classical assumptions, because of course, assumptions are not limited to the quantum domain. A practically highly relevant assumption, which are commonly used in practice, are computational assumptions. And intuitively, these assumptions consist of 2 parts. First, we will assume that there's some computationally difficult problem. Many such assumptions are known. For example, we might assume that finding the prime factors of an integer is difficult. Second, we will then assume that the attacker has limited computational resources or time, namely not enough to solve the difficult problem. Such assumptions go very well on criteria 1. It is often easy to execute such protocols. Indeed, we will always like such assumptions for some tasks in practice, since we can use them together with classical communication. How about criteria 2 and 3? It is actually often not known whether the assumptions are completely valid, in the sense that this problem truly is computationally difficult. This is the case for factoring. It could very well be that there is an efficient classical algorithm to factor numbers, it just hasn't been discovered yet. So it is in fact often unknown how many resources the adversary really needs. We also have to ask ourselves, how long do these assumptions remain valid? In the case of factoring, for example, we do know that the quantum computer can factor efficiently and break such protocols retroactively. Another assumption that is made classically, is less practical but quite beautiful, is that Alice and Bob are divided into several agents or servers which cannot talk to each other during the course of the protocol. Such a ban on communication could, for example, be achieved because the agents are far apart, and hence, since there's a limit on the speed of light, they cannot communicate within a certain time frame. Such assumptions need quite some resources. We need multiple agents to be implemented. But it could be impossibly hard for the adversary to break them within some time window, because the speed of light puts an inherent limit on how quickly we can communicate. Are we actually making an assumption then? Yes, this counts as an assumption, since the fact that we assume that there are multiple agents. And this becomes most evident when considering criteria 3. Namely, when we ask ourselves, what happens if the assumption becomes invalid? Clearly, the agents will always be able to communicate eventually, and security breaks down disastrously when that happens. For this reason, protocols that exploit these assumptions are generally only interesting if we really only need security of the protocol, and importantly, also all subsequent protocols built on top of them, for a very short time. Such times can, to some extent, be extended by continuous communication to maintain security over time, but this is really quite inefficient in practice. Another set of assumptions, which is particularly appealing in the quantum case, is that the adversary cannot perform operations on more than k qubits at a time. Security remains valid as long as this assumption remains valid. We will not discuss this here, but you can find pointers to the literature in the lecture notes. Next to operations, We could, of course, also consider limitations on other resources. We could, of course, use such assumptions in conjunction with options 2 and 3, but here we will always apply it to option 1. Let us again start with the classical case. Already in the 90s, Uli Maurer proposed a very nice model, namely to assume that the adversary's ability to store information is limited. This model was applied to assuming that classical storage is limited. Clearly, assuming that the adversary can only store a certain number of classical bits is not particularly realistic, given that classical storage is cheap and plentiful. Most significantly, however, this assumption did not store very well on criterion 2 in the classical case. Namely, the gap between what the honest party needs to run the protocol and what the adversaries needs to in order to break it is very small. Concretely, if the honest parties needed to store n qubits in the protocol, then an adversary, a dishonest party, needed to store only roughly n squared in order to break it. Of course, one could also consider such assumptions in the quantum domain. Storing quantum bits is, after all, generally quite difficult. Currently, storage times are on the order of seconds, and we can only store a handful of qubits. This assumption has been captured by the so-called bounded quantum storage model, or more generally, the noisy storage model. Counting qubits is not always very informative for quantum memory devices, whose state space is in principle sometimes even infinite dimensional, yet we know that the adversary can store hardly any information in them. This is the case for considering noisy as opposed to just bounded quantum storage. The nice thing about these models is that they score well on all criteria. We will see that it is easy to execute such protocols. In fact, you need essentially the same hardware as for QKD. In particular, we will not need any quantum storage to run the protocols. However, at the same time, it is very difficult to break security. If we transmit n qubits, then the adversary needs more than n minus order log n to square them. Finally, the assumption is indeed future-proof. Even if the adversary buys a much larger quantum storage device later, there's nothing he can do. There's no way for him to retroactively break the protocol. As you can see, there are thus many ways in which quite realistic assumptions can evade the impossibility proofs to solve practically relevant problems. In fact, we know that in principle, any assumption that limits the adversary's entanglement with the honest party would do the trick. Here we will now investigate the noisy storage model in detail. But maybe you have some new ideas on good assumptions yourself.